The diagram shows the unit square on a plane and its image after the linear transformation applied to it. So here we have the unit square and then this transformation is applied to it. A, write down the transformation matrix, calculate the eigenvalues and the eigenvectors of this transformation, and represent the eigenspans on a diagram. Okay, so in order to find the matrix, all you need to do is look at the base unit vectors, which are 1, 0 and 0, 1, and see where they go to. So what 1, 0 goes to this point here, A dash, which is 4, 3. So 1, 0 goes to 4, 3. And then 0, 1 will go to C dash, which is going to be 1.12. So it becomes 1, 2. And therefore, the transformation matrix will be A, which is 4, 3, 1, 2. Right, in order to find the eigenvalues, and we'll have a look, see what these actually mean when we look at the diagram in a minute. So we need to find a vector xn, yn, such that axn, the matrix times the vector, will be equal to some value, which is called the eigenvalue, times the same vector. So we have here, if we rearrange this, we've got A times the vector minus lambda I x, the vector is equal to 0. And therefore A minus lambda I x n x is equal to 0. And then if we take the discriminant of this matrix, and the discriminant would have to be equal to 0 in order to give a non-trivial solution. So A minus lambda I is equal to 0. Let's see how that works. So our matrix minus lambda times 1, 0, 0, 1 will have to be equal to 0. So that gives a discriminant of 4 minus lambda minus 1, because it's minus minus 1, and then 3 minus lambda times 0, which will give you 3, and then 2 minus lambda will give you equal to 0. So finding the discriminant, so that's these two minus these two. So that's 4 minus lambda, 2 minus lambda, minus 1 times 3 is equal to 0. Expanding, we're going to get 8 minus 6 lambda plus lambda squared minus 3 is equal to 0, and then making that into a quadratic, we get lambda squared minus 6 lambda plus 5 is equal to 0. So either now you use the quadratic formula, but this one actually does factorize quite easily. So it's that lambda minus 1, lambda minus 5. So this will give the eigenvalues of lambda 1 being 1 and lambda 2 being equal to 5. Now if we now substitute it back into this, so when lambda 1 is equal to 1, we've got the matrix times our vector, which I'm going to call x1, y1, will be equal to 1 times x1, y1. So ax is equal to lambda times x. Okay, so that will give 4x plus y1. 4x1 plus y1 is equal to x1. Okay, and then we get 3x1 times 2y1 is equal to y1. Now, we just need y1 in terms of x1, so this will give, in both cases, it will give the y1 is equal to minus 3x1. So that means the eigenvector will be, if this one is 1, if x1 is 1, then y1 will be minus 3. But any multiple of that will also be a eigenvector, so we can put a k in front. Then doing it for the other eigenvalue, so when lambda 2 is equal to 5, we get ax is equal to lambda x by again. So doing the same thing, but this time taking 5 as our value of lambda. Again, 4x2 plus y2 is equal to 5x2. 3x2 plus 2y2 is equal to 5y2. And this will give y2 is 1 times x2. So that eigenvector will be v2 will be 1, because if this is 1, then y2 would have to be 1, but any multiple of that will also give the eigenvector. Okay, so that shows you how to find the eigenvectors. Now, you're asked to represent these, so I did this on a GeoGebra app, so we'll just jump to that. So here we have our matrix, and here we have the transformation. Here we actually have the matrices times the unit square that will give the image. Okay, and then if I click on here, then here we get the first one, which is 1 minus 3, which is down here, and then we get the other one here, which is 1, 1. But if I change k to a different value, anything value along that will go along those lines. So any point on those lines, okay, will not be rotated or anything. They'll just be stretched along the line a little bit further. And these are called eigenvectors. So all these are eigenvectors. Now, this GeoGebra app I will put in the link of the video. You should be wary that you can actually change the actual values of b, and then it will work out the eigenvalues for you if there are any. No, so you're not always going to get them, of course. Okay. Here you only got one because you've got a repeated root. Okay, so you can see that. So you can have a play around with this. This link of this GeoGebra app I will put in the notes of the video. Okay, this has been a video to show you how to find eigenvalues and eigenvectors and to represent them on a plane. I hope you've understood, and I thank you very much for watching, and I'd ask you if you could try to subscribe to my channel.